Okay, so I'm just going to wait a minute so that people can join. Okay, let's start. Hi and welcome to this Danish Sound Cluster webinar. The subject of today is personalization of user needs, and we'll talk about smartphone connected hearing aids that makes it possible to collect real-world data from users. A few practical things before we start. Do remember to ask questions because we have the speakers here for the same thing. And when you ask questions, please do it in the Q&A session because that's a good way for us to handle the questions. We will take some questions after each presentation, and then we will do a question session in the end as well, where we will probably answer some of the broader questions. But you can ask questions in the Q&A chat all the way through the presentations. Then we also have a normal chat, you can say, where you can post relevant links or any comments you may have or something like that. And then I have to inform you that we are recording this webinar and the recordings will be sent to you afterwards along with the presentations from the speakers. We also have a questionnaire and we would very much like your help to fill that out. It's going to pop up at the end of the session and that will help us improve in future webinars. So please spend a few minutes doing that. We are very fortunate to have with us today Niels Pontoppidan from Eindhoven's Research Center, and Niels will be the moderator of today's webinar. And I will hand over to him actually now for him to introduce our speakers and the topic in general. So please go ahead, Niels.
Thank you very much, Stine, and welcome to all of you for this webinar today on personalization of user needs. And we have two distinguished speakers with us today. We have Alessandro Pasta from Demant, and we have Professor Bert de Vries from TU Eindhoven. And before I talk a little bit more what their contributions to the field are, I would just like to just recap what this is all about, because this is about personalization of hearing aids, and that's actually something that has been an active research topic for years, for ages, for decades. But as I sometimes say, back in the past, back in the days, this was something that was done with pen and paper. People went around with their diary and then they noted when it worked and when it didn't work. And since the number of adjustable parameters in hearing aids have grown over the last 2-3 decades, this is simply an intractable way to do this today, because there are too many parameters to keep track of. The end users really do not have any chance of remembering what the difference between different programs and different settings are. And they also have a limited vocabulary just for describing the situations and that they were in. So it is, if we are not using modern techniques based on data and advanced inference, it's really an intractable problem where we simply do not get to the bottom of this. And luckily, today we have Alessandro and Bert with us, and they will give their account of how they are actually working with data and inference to understand user preferences and user needs, so that we in the future can have a far more personalized hearing aid settings. So our first speaker today, that's Dr. Alessandro Pasta. He will be talking about clustering users based on hearing aids and explanatory analysis of real-world data. And Alessandro recently obtained his PhD from DTU here in Denmark, and I was honored and lucky to be his co-supervisor in this. And today he is now a senior data scientist with Demant, the company behind Oticon brand. Then after Alessandro, then Professor Bert de Vries from the Technical University of Eindhoven will give his talk on a Bayesian approach to hearing aid personalization. And Bert has been for 10 years with the TU Eindhoven, and then for even more impressive, 20 years with the hearing industry. So both into the science and also hearing aid development. And Bert has actually been pursuing, I know from having seen him giving talks during this period, pursuing personalization for many, many years and applying Bayesian principles to achieve that. And now he runs a group at the TU Eindhoven where they apply Bayesian principles to real-world engineering problems. So that is what we are so lucky to have on board for you today. And with that, I would like to give the word to Alessandro and for your talk, and then we will have the questions after that, and then it will be the time for Bert's talk. Here you go, Alessandro.
Thank you, Niels. And hi, everyone. I'll share the screen. Hi, everyone. I'm Alessandro, and thanks, Niels, for the introduction. Today, I would like to talk to you about a study that I've been conducting during my PhD. We analyze data logged through smartphone-connected hearing aids to better understand how users use their hearing aids. But if we take a few steps back, globally, 20% of people suffer from some degree of hearing loss. And this percentage has been increasing in the last 30 years. And partly due to the aging of the population, this percentage is expected to increase in the coming 30 years. The World Health Organization is estimating that by 2050, around 25% of the population will have some degree of hearing loss. And not only we know that hearing loss has a high and increasing prevalence, but we also know that hearing loss has profound consequences on a broad range of dimensions. It has been shown that hearing loss has consequences both on an individual level, resulting in, for instance, lower physical abilities and psychological status, but it also has consequences on a societal level, resulting in higher medical and non-medical expenditures. For most of the people suffering from hearing loss, the consequences of hearing loss can be reduced through some hearing technologies, among which there are hearing aids. And in addition to improving the audibility of sounds, hearing aids have proven benefits. For instance, hearing aid use has been shown to improve the cognition of hearing aid owners, but also is being associated with lower risk for dementia and with an overall greater health-related quality of life. However, for a successful hearing aid adoption, there is not only a need for a good intervention to be provided and a good impact on the conditions of the hearing aid owner, but also there needs to be some compliance of the user with the hearing aid treatment. And there has been a lot of studies in the past assessing how much hearing aid have been used. And this has mainly been done through self-reported measures, such as interviews or surveys or diaries. However, there are studies that show that these self-reported measures tend to lead to inaccurate and over-reported hearing aid use. In contrast, smartphone-connected hearing aids enable objective data logging. And that not only enables logging data with a higher temporal resolution, meaning that we can look into hourly patterns of use and not only daily patterns of use, but it also enables a longitudinal assessment of hearing aid use by looking at data across days or weeks. And thanks to the widespread adoption of smartphones among the older adults, it also enables accessing data for a larger sample of users than ever before. Traditionally, we have also seen that when evaluating the usage of hearing aids, the main question that researchers have tried to answer is how much are hearing aids used? And this amount of hearing aid use has been regarded as a sort of treatment success, indicator of treatment success. However, even though it's correlated with satisfaction, we also know that this doesn't really give us a complete picture. And through objective data logging, we can not only look into how much are hearing aids used throughout the day, for instance, but also on how are hearing aids used by looking at hourly patterns of use throughout the day. Additionally, even though the industry tends to look into users and tends to care for the average user without too much of a personalization, users seem to use the hearing aids differently among each other. And objective data logging allows us to both identify and also quantify, based on a large sample, the different types of users based on how these users have been using the hearing aids during a study, for instance. And finally, previous studies tend to represent users, an individual user, by their average use throughout the days for which the study has been running. However, we also wish to adopt a metric that also consider the within user variability, so the day-to-day variability in the hearing aid use of an individual user. In our study, we've been firstly exploring the amount of hearing aid use based on objective data logging. We have then analyzed hourly patterns of hearing aid use in order to identify typical days of hearing aid use. We have then clustered users based on how these users have been using the hearing aids during the duration of the study. And finally, we have validated the user clustering by training a supervised model to predict the user clustering to which a user belongs. So we did that by collecting data over 4 months, from June to September 2020. We specifically analyzed more than 400,000 days of hearing aid use logged by more than 15,000 users. And we first explored the amount of hearing aid use of these users. We looked first into the average daily amount of hearing aid use per user. And we can see that on average, our users use the hearing aids for around 10 hours per day. When looking at the literature, this value is similar or slightly larger than previous studies that measured hearing aid use through objective measures. We then looked into the within user standard deviation of the hearing aid use amount. So to what extent the users vary from day to day. And we saw that on average, users had a within user standard deviation of around 3.8 hours, indicating that their usage tends to vary from day to day. And if we merge the two previous graphs, then we can see that the middle 50% of users tends to use the hearing aids from 8 to 12 hours per day. But there is a remaining 50% of users, which is using the hearing aids either less than 8 hours per day or more than 12 hours per day. And when looking at the within user standard deviation of these users, we can see that these light or heavy users tend to use the hearing aids more consistently than the middle 50% of users. So they have a lower day-to-day variability. We then further explore the patterns of hearing aid use by clustering days of hearing aid use based on the hourly patterns of use in each day. So our data set looked something like this. We had our 400 days, one per row. And then each row was a date for a specific user. And we had information about the usage from 6 in the morning to 23 in the evening. So a specific cell here would be the hourly amount from 0 to 60 minutes of hearing aid use. For instance, in this case, at 6 a.m. on the 1st of July for a specific user. We clustered this data based on a k-means algorithm and we found the 3 cluster solution to be the most suitable. Here you can visualize all our days of hearing aid use plotted by the first and second principal components, where you can see that more to the right, we see lighter use compared to the days that are plotted on the left. So heavier use on the left and lighter use on the right. And then we can see days with the earlier use on the top compared to days with later use during the day on the bottom. And if we look at the average position of these 3 clusters, we can have a graph like the following. So here we have a y-axis where we show the average usage of the hearing aids in minutes per hour, so from 6 to 60 minutes. And then we have the 18 hours of the day from 6 in the morning to 23 in the evening in the x-axis. We can see that there is a cluster, the red one, which groups days of hearing aid usage where the hearing aid has been turned on in the morning, used uninterruptedly throughout the day, and then turned off in the evening hours. We call that day full day of hearing aid use. And this accounts for around 44% of the days in our dataset. We can then see an orange or yellow day of hearing aid use that groups days in which the hearing aids have been turned on later in the morning, used uninterruptedly throughout the day, and then turned off in the evening. We call that day afternoon day of hearing aid use. Finally, we can see a blue cluster that groups days of hearing aid use in which hearing aids are used in isolated occasion during the day with a peak in the evening hours. We call that cluster sporadic evening hearing aid use. And now that we have 3 clusters, we can represent the users, our 15,000 users, by the time spent in each of these 3 typical days of hearing aid use. So by using a matrix that accounts for the within user standard deviation, the day-to-day variability in hearing aid use. So as a third step, we cluster the users based on how they spend their time within each of the 3 typical days of hearing aid use. So our data at this stage looked something like this. We had 15,000 users, 1 per row, and then each user was represented by the percentage of time spent within each day type. So this user has been spending 60% of his time in day type 1, the full day of hearing aid use. Based on this data, we tried different clustering algorithms and we selected HDB scan as the best performing one. HDB scan identified the 3 cluster solution to be the most suitable one. And if we look at the 3 user groups resulting from this clustering process, here we can see the days experienced by each of the 3 user groups. And the principal components are the same as before. So each dot is a day. And what we can see is that users, the 3 groups of users, tend to have very distinct days among each other. So they tend to use the hearing aids differently among each other. And if you look at the average for each user group, we can look at the proportion of time spent in each of the 3 day types per user group. And we can see that the first user group A, accounts for almost 50% of our users and groups users that predominantly had full days of hearing aid use. To some extent, they had afternoon days of hearing aid use and sporadic evening hearing aid use. We then have a second user group B, which groups users that predominantly had afternoon hearing aid use days. And the third group that groups users which had, on average, predominant sporadic evening hearing aid use. Finally, we have a 15% of users, which was labeled as atypical by our clustering algorithm, exhibiting a pattern of usage which is not similar to other users, and therefore was not placed in any of these three clusters. Overall, we can see that the users belonging to the three groups exhibited both a predominant daily pattern of hearing aid use, but also some day-to-day variation. Indeed, the predominant day type accounted for around 60% for each of the three user groups. And it should be noted that this day-to-day variation might not emerge in studies that are based on retrospective assessments and therefore suffer from some recall bias. Finally, to validate the quality of the user clustering, we trained the model to predict the user group label of a specific user based on his or her average day of hearing aid use. And for doing that, we trained an ensemble of three classifiers: a logistic regression, XGBoost, and a neural network. And when looking at the accuracy of our ensemble of classifiers, we can see that the classifier is able to predict correctly the cluster to which a new user belongs 86% of the time. And if we look at the raw CAUC score, specifically the micro average, we can see that it's around 0.98, validating the user clustering partition. We can also look more specifically into which user group is our model able to predict the best. And what stands out is probably the orange line, which is the one that is showing the performance of our atypical or noisy users. So users that tend to be atypical and not placed in any cluster. Those are the ones that our classifiers is most struggling at classifying, while the other user groups tend to be predictive with a good accuracy. So all in all, we analyzed the amount of hearing aid use based on data logged by smartphone connected hearing aids. We found that hearing aids have been used for around 10 hours per day by our users in the sample. And we also found a substantial between, but also within user variation. We then looked into the hourly patterns of hearing aid use, and we identified 3 typical days of hearing aid use: a full day of hearing aid use, an afternoon day of hearing aid use, and a day of sporadic evening hearing aid use. We then used that information to cluster users based on their hourly use patterns. And we found 3 user groups, each having a predominant daily pattern of hearing aid use. Finally, we validated our user grouping, and we trained a model that was able to predict the user group label of a new user with a 86% accuracy. All in all, grouping users based on their pattern of use enables both a deeper understanding of our users' behavior and needs, but also a long-term, more personalized solution. And in terms of future work, it would be very interesting to firstly look into complementing this data with more subjective evaluations of the experience of our users. Indeed, for instance, we have a cluster of users that tends to use their hearing aids sporadically and mainly in the evening. It would be interesting to look into whether these users are behaving like that because they're not satisfied with their hearing aids and therefore are maybe likely to put their hearing aids in a drawer for the rest of their lives, or if they're behaving like that because they're less dependent on their hearing aids and therefore only need them in very specific and complex occasions. Finally, it would be interesting to complement this study and better specify the characteristics of our groups by looking at, for instance, what the age or what the hearing loss profile is for our different groups of users behaving differently. Thank you for your attention.
Thank you very much, Alessandro. I can see that we have a first question from Tim Schuf, and I'll just read it out. Do you expect to see age differences in the clustering? For example, the afternoon users might be younger than the full day users because they might just wake up later.
Exactly, that's a very good question, and that's what I basically was referring to in the very last slide. It would be very nice to complement this data with data about, for instance, the age of our users. There might be differences in terms of, for instance, the age that also kind of drives the activities of the users. So I expect there might be some differences, but we haven't looked into that. We didn't have the data for that. But it would be a very interesting follow-up analysis to conduct. We did look into whether the clusters had whether the different days were more frequent, for instance, in weekends compared to weekdays. And there was an effect, but not a very large effect. So that didn't seem to drive the difference in terms of day of hearing aid use. So maybe it's more about who the user is and what are the activities that the user usually undertakes.
Thank you. And we have a question from Ian Biggins. Do you see any individuals who transition abruptly from being users to non-users? If so, can you predict who will try hearing aids for a while, but is ultimately at risk of giving up on them?
That's also a very nice, interesting question. We haven't looked into the kind of evolution of usage throughout the time for our users, but we might be able to look in to see that users change in the way they use the hearing aids and maybe transition from one user group to another, and therefore might need more attention, for instance, by the clinician, or maybe they're instead learning about how to use the hearing aids and they start using them more because they managed to get acquainted with them.
There are some of you that are putting your questions in the chat. Please put them in the question and answer, but I'll try to keep track of it. It disappeared. Sorry, 1 second. Okay, so Bert Ayat asks, does the usage include talking over mobile networks?
Sorry, can you repeat the question?
Does the usage include talking over mobile networks?
Yes, it does. So the usage includes basically the time. It looks into the time the hearing aids have been turned on. So if the hearing aid user is talking on mobile networks by having the hearing aids on, that's included.
And we have another question from Benjamin Scholz. Which features did you use for the prediction model to predict the user group?
Which feature? So we tried three different models, and the ones that I mentioned, so XGBoost, logistic regression, and the neural network, and then we combined them so that they could kind of vote, and the most voted group was the one that was assigned to the user. In case there was a tie in the votes, then the best performing model was having a saying on what was the group of the user, so the prediction basically.
And we have another one from Maya Bülow. Did you also look for variations during the different weekdays? Example, different activity during weekends?
Yes, as I mentioned earlier, we looked into whether a specific day, it could be like, for instance, the full day of hearing aid use was more likely to happen during a weekend, or more likely maybe during weekdays. And there was a difference, as I mentioned, but not a large difference that was kind of driving the hearing aid usage. So it's not only that, although that plays a role in the days of hearing aid use in our dataset.
Thanks. And then we have another question from Sebastian Ausley, and we had it a little bit back and forth, but first, congratulations on a very nice study. And then, do you have a measure of listening effort in your study that might be able to explain the non-use in some cases?
We don't in this study. We didn't really collect listening effort as such, but it would be really interesting to complement basically this study with more information about the user and also the activities that the user undergoes, and also more information about the experience, like listening effort, for instance. So it's a very good point. We didn't have that in our study.
I think that I can add here that it is actually some of the things that we have been talking about also. So these are really interesting directions that we are going into. I cannot see any more questions, so I'll take the opportunity to shoot one for myself. You're talking about the preferences and what you can learn, and here we're looking into different usage patterns. So. And when it's used, do you think that will also be able to tell us something about the user needs? Simply, do you have an expectation that these different groups have need for really different kind of signal processing algorithms?
I do think that this information about how the hearing aids have been used, complemented with more information about either preferences or more information about the user to better understand what the user is, which challenges the user is coping with, could help at least explaining part of the preferred settings. It's probably not the only variable that might explain it, but I think it could help getting a better understanding of who the user is by looking into how they make use of our devices. And also maybe quantifying this also help like quantify the market and the pool of our users by placing numbers on how big are the different types of users.
Thank you. And then as the last question, there's a follow-up question from Benjamin Schultz. He says, my question was more about the input to the model. What information such as hearing loss, amplification, etc., did the model use to make its prediction?
Yes, so the input to that model was simply the average use for the specific user. So for that model, we took the days of usage and of a specific user, and we averaged it. So we had a row that tells us about the average usage for that user, meaning average usage throughout the day. So from 6 in the morning to 23 in the evening. And we use simply that to train the model and evaluate the partitioning. So we didn't add information about characteristics related to the user.
Thank you. So that's it. Thank you very much, Alessandro, for giving once again a nice presentation and for also being part of a really nice discussion. And then we will give the word to Professor Bert de Vries from TU Eindhoven, who will talk about So I have a Bayesian approach to hearing aid personalization. So here we go.
All right, thank you, Niels. And also thank you, Alessandro, for a really great presentation. I hope you can see my screen. It should say Bayesian approach to hearing aid personalization. And let me go to the first slide. I'm going to set up the problem. So here's a hearing aid client listening to a hearing aid device. And so assume that, well, I mean, people go to the hearing aid dispenser, they're usually very happy, but something always happens, right? 3 weeks later, you're in a restaurant and you can't hear your conversation partner or something else. If this problem persists, well, you go back to your hearing aid dispenser. And yeah, well, then the problem that you had is not really reproducible. So it's very questionable if it can be resolved there. So if more and more of these problems persist, it goes back to the drawing table of the engineers at Demant or GN or wherever, and they start working in MATLAB, and that takes half a year, and then it has to be recoded and tested and sales, and so it takes a year or 2 years to close this design loop from an idea to idea, or from product to product, right? Because there's, what is it, 300, 400, 500 people are here in the company in the middle of this design loop. And by that time, this problem of this user who couldn't hear her conversation partner, well, our reaction is just too late. And it is a big contrast to what happens in the real world. If we try to learn something, learning how to ride a bike, it proceeds completely automated, right? There's no engineers in the loop. It's in real time. It's a real-time design loop. I ride the bike, and when I fall, I make a correction, and I just play until I learn it. There's no off-site design that gets tested, or there's also another big database or deep learning or anything. It just seems a completely spontaneous process. And mind you that the brain is also an algorithm designer for hearing. When we are born, we don't understand English or Danish or Dutch. And just through interactions with our environment, I learn Dutch or English. And if need be, I can learn Spanish. And it's just by interacting, and so we can learn anything, and it's a spontaneous process. So what's on the right-hand side is what's sort of my inspiration for a new way of designing hearing aids in situ, so under field conditions, by hearing aid clients just having some interaction with their device or with their environment, and then over time this device should improve. Right, so I'd like to go away from the idea of posing the question as hearing aid design in a company as, okay, let's design the best possible hearing aid, to another question, which is under situated conditions, whenever there is some problem, what's the best way to react? Because that's how we learn really in the field. Now, if you then take a very, let's say, a physics-based look and go very fundamental. So how do spontaneous computations even take place in the real world and in the brain or anywhere? Then from your physics classes or chemistry classes in high school, you may remember there's something like Gibbs free energy. And it is said that, a chemical process or process is spontaneous if the Gibbs free energy after the reaction is lower than before. You may remember that. And indeed, in nature, free energy, Gibbs free energy decreases everywhere. That is the driving force of anything that happens in nature. It turns out that you can write down this formula for Gibbs free energy, which I wrote here as an enthalpy, which is an energy, minus a temperature times an entropy. You can also write that down, and now I write it down in information theoretic terms. And the formula doesn't matter at all for this presentation, but I can write it down as an energy minus an entropy. And Q and P are probability distributions. So now we're dealing with information processing, variables and probabilities and so forth. And this is called a variational free energy. And there is a fellow called Carl Friston. You should look him up on the internet. He is by far the most influential neuroscientist alive. Currently, he works in London, UCL, and he's developed a theory which is called the Frenetic Principle. And I'm just reading this now here. The Frenetic Principle states that all biological processes, including perception, learning, action, decision-making, structural adaptation, everything, really everything, is governed by spontaneous variational free energy minimization. What that means is that Carl Friston says that anything that happens in the brain is just minimization of this free energy function, of this thing. I have to, there's something on my, I don't know how to get, sorry. There's something on my screen that you don't see, but I want to get rid of it. I'm going to the next slide. You can say two things about this free energy principle that's interesting. On the one hand, it is just a restatement of something very fundamental in physics, which is called the least action principle. The least action principle just says everything in nature, all the processes have its root in the fact that energy differences of any kind are equalized as fast as possible. That's how nature rolls. You can derive quantum mechanics from it, classical mechanics. So you can derive Newton's laws and Maxwell's laws. You can derive almost all of physics from this principle of least action. On the other hand, if we minimize this variational free energy functional, so the information theoretic formulation of this principle, then that implements something that's called Bayes' rule. And Bayes' rule is really the fundamental rule for information processing and machine learning. So in short, what Carl Friston says is brains just follow the laws of physics, right? They follow, well, basically the principle of least action. So how could it be anything else? The interesting thing is that this, following the laws of physics, leads to approximately Bayesian inference. In other words, leads to automated optimal information processing. I put in between brackets approximately because we don't find the global minimum of this free energy functional, right? But we minimize it, but we are not perfect at minimizing this free energy principle. But we are approximate optimal information processing beasts. And we are so because we follow the laws of physics. That's the amazing thing. There's a lot of proof for this, theoretical proof, experimental proof. Now, if I just make that a bit more concrete, so what's really happening in the brain is when I interact with the environment, when I want to learn a skill, I have sensors like eyes and ears, and I have actuators, muscles to turn my head to look somewhere else. And well, there's lots. I mean, there's also muscles in the ear, and we can move closer to an object to get a better hear of an object. So what we do is we kind of go through what's called an action perception loop. Both perception and action are based on free energy minimization. Again, don't worry about these formulas. It turns out that if I look at these formulas, because I can actually write this down, then minimization of free energy is the only thing that's going on. And so it's a one solution approach to all problems. Basically, when I learn how to ride a bike, once I fall, I make an action with the handlebars or shift my point of gravity. There are two purposes for doing that. One is to solve the problem, to stay upright. But if I don't know what the effect is of turning the, let's say, the point of gravity on the whole system of me on the bike, then I need to learn a model of basically of the environment, of how a bike falls in an environment, etc. I need to, and in that case, my action is to collect observations that are most informative about what's going on in the environment. That means they are what we call, well, they maximize information gain, or they are seeking, they are epistemic, they seek information. In the brain, so this process of action perception is works on every problem. So in the beginning, my actions are mostly tailored towards getting observations that learn me, that allow me to learn how the world works. And then once I have a model of how the world works, I can predict how the world works under my actions, and I can keep myself upright. So I slowly move from, let's say, from learning a good model about the world to using that model to basically keep me upright or for whatever utility I have. And I do that with every problem. And it's completely transparent. The brain doesn't really know what it's doing. It's just minimizing free energy functional. This here, to put basically what's in the brain, the math in a watch or in a hearing aid or in a watch is the purpose of my lab at the university. We want to build synthetic free energy principle based AI, artificial intelligence agents. What should these agents do? Well, whatever we tell them to do. They should interact with the world. They may put actions onto the world. These actions may change the observations. These observations are processed by perception, leading to new actions. So we have this real-time loop. And by constructing a particular way of our free energy functional, this system should converge to the utility that we want, namely riding a bike or anything. And in my case, to learning a hearing aid. It should be personalized, right? So the system that I work on is we have this agent in a watch or in a hearing aid. This agent can take actions. What are actions? Actions are new parameter settings in a hearing aid, or putting a completely new algorithm in a hearing aid. If I change my algorithm or I change my parameter settings, well, then what the user or the client hears will change. And the client can give a gesture that could be just a thumbs up or a thumbs down. That could as simple as a pen click on what he thinks of that proposed action. And then this is processed, and that may lead to new actions, new proposals, and so forth. Now, if I put a constraint in this free energy functional that in the future, the client will only have, let's say, green thumbs up, then minimization of this free energy functional will lead to actions that have, and there's no other way, but it will lead eventually to the client being happy, because that's just how the free energy functional is constructed. It will automatically design a hearing aid. And in sort of the same way, in a real-time loop rather than a loop that takes a year, because the designer now is, basically the designer is this, the engineers and audiologists and everybody in the company is now packed in a computational formula in this iPhone, right? So you can send out a patient with this iPhone into the field, and whenever she is unhappy, you tell her, you press this button or shake your head or do whatever, a little thing. in response, you will hear a different sound, and you get, when you're happy, you don't do anything, and when you're unhappy, you click again, and you just click until you're happy and move on to 2 days later when there is the next problem, and you click a few times and until you solve it and you move on. And that's how this patient will design her hearing aid, or so that's the whole goal of it, right? So there are two questions when you view hearing aid design as this in situ conversation between a hearing aid patient and some agent. Namely, what's this free energy functional, or in other words, what is this, what we call here this probability distribution P? And the next thing is, how do I minimize it? How do I minimize this free energy functional? Because that's the only thing going on. So these are the two big research questions. Which model, which probabilistic model should be inside the agent? Once I put the model inside the agent, how do I minimize the free energy? And again, we looked at how the brain does it. And so what's inside the brain, right? And in order to set that up, I'll ask you a question, namely, what do you see here? And this is, by the way, a painting, or not? I think it's a painting called The Gardener. And you see here a vegetable bowl, and at least very likely. And if I ask you, what do you see here? You will say, well, that's a gardener. That's just sort of a face of somebody, right? So why on the right-hand side don't you see an upside down vegetable bowl, a bowl of vegetables first? Well, the reason is that the brain is not just some receiving organ that does pattern recognition on pixels. The brain is a very active organ that generates a hypothesis of what we see. And what you actually see, what you actually perceive, is some fusion of your hypothesis of what you see and the sensory inputs. Now, because we see in life a lot more straight faces than upside down vegetable bowls, if we see the picture on the right, we will rather see the face than upside down vegetables, because it doesn't occur very much in nature. On the other hand, on the left hand side, a straight up vegetable bowl is something that we have a high probability for seeing in nature. So that's a very feasible hypothesis that the brain makes. And so when the sensory input comes in, and for the left picture, you see this vegetable bowl and not an upside down face. So, and there's already some 50 years ago, based on, and this is just, what you just saw is just, let's say, an experimental confirmation of that. But every good controller or regulator of a system must be a model of that system. In other words, the brain has a model inside, a model for sensory inputs. It's a generative organ. So we know now what we should put inside this agent if it's going to function like a brain that's going to design some algorithm. The second question is, how do we minimize the free energy in that model? And I'm going to skip that, other than saying, well, we have devised, and it's based on basically some theory that people do this in machine learning and in information theory. They call them Bayesian networks or factor graphs. And you can minimize a free energy by building a network of this model, a graph representation. And in this graph representation, the nodes send messages to each other. And this is a spontaneous process that minimizes free energy. And I'd just like to draw attention to the fact that it's not a coincidence that the brain is a network of nodes, and all processing is just a process of, well, these nodes, the neurons, sending messages to each other, action potentials, right? So we implement that very much also inspired by how the brain works. Of course, there's a whole lot of computational theory behind it, and you can read that in our papers. But first order approximation is we build a graph, and free energy is completely automatable. We can write a toolbox for that, and it happens by passing messages. So now we know what to do. We know what model we should put in, and we know how to minimize free energy. There's papers on this. And so already about 4 or 5 years ago, we built a network. And here on the right hand, you see this network. This is a model. And we said, okay, the observations are user sensations, and the user is only happy when the signal is audible and when it's presented at the right loudness level. And then we minimize free energy in this network. And we minimize the free energy at 3 different levels, to states inside this model that may change very fast at millisecond level, and that leads to the algorithm signal processing. It turns out, you can check that, this is a dynamic range compressor. And we didn't design a dynamic range compressor. We just said, oh, the user is only going to be happy when the loudness level is what she expects to hear. And it turns out to be dynamic range compressor. We also minimize free energy with respect to variables that change a lot slower. In fact, that's called parameter estimation in engineering. In hearing aid parlance, we would call that fitting. And in, let's say, in neuroscience, you call it learning. And so the interesting thing is that also fitting, hearing aid fitting, is just a process of message passing in the same graph. And you can even change the free energy with respect to the structure of the network. We also do that in our brain. We lose 10,000 neurons per day. The structure of the brain changes. And I mean, the most drastically way that the structure of the brain changes is just by procreation, right? And natural selection is actually free energy minimization over a very long time span. It turns out that if we do that as well, we basically design an algorithm, the dynamic range compressor. But crucially, in hearing aid design, we think of designing the algorithm as a different task than fitting the algorithm, fitting the parameters, which is a different task, again, as executing the algorithm in the field. In this framework, it's all the same, because perception, learning, and evolution is just free energy minimization. And in our framework, it's just message passing in a graph. So we have one framework here that basically represents the entire, let's say, all the tasks that are needed to design a hearing aid algorithm. Design the algorithm, fit it, and run it. And it's personalized because it's a function of feedback of the user. So everybody who walks around with this iPhone, with their own iPhone, gets their own algorithm. Everybody has their own free energy functional. Now, based on this concept, we've worked for a long time, because this is under the hood, quite difficult with lots of math. And so here's a paper that was already published in 2016, and this is a paper. I'm sorry, I'm not sure if you can hear something, or if Zoom allows me to play the example, but we've been working on this now for many years, and so this whole concept has evolved, and we have a new proposals. But in the end, it's still a graph that goes inside the hearing aid. There's an input for microphones, there's an output, and there's also an input for user feedback. And this is a network, and we just do one thing in this network: variational free energy minimization by message passing. We get about, this is not very officially verified in large experiments, but we seem to get about 4 dB signal to noise ratio improvement at the moment with this approach. I could try to play the example, but I don't think, or I haven't seen that Zoom actually allows me to stream that through the network. So I will make that available offline. And if you want to read everything about it and also see where you can download code, there's a recent paper in March 2022. So this is the most recent version. That is all I have to say, because I didn't want to make it very technical. And so I'm open for questions, if you will. Thank you.
Thank you, Bert. And we have already the first question in the Q&A. That's Birger Schneider, who asks, how do you ensure that at the end of the improving process, the user obtains an optimal solution? In music, it is a known fact that some people set their preferences to high bass or high treble. Do we not risk that individuals achieve preference-based solutions that are not necessarily optimal in use?
Yeah. It depends, of course, what you mean by optimal. The optimal is always in reference to some criterion that you want to maximize or minimize. There's two ways we do this, right? Well, first of all, I like to say that none of us are optimal, right? I mean, the human brain is not an optimal machine. I'm certainly not optimal. And we are not optimal hearing machines. So our goal is not in principle to build the optimal hearing aid. My goal is here to design a mechanism that whenever the user has a problem, I have an optimal response, and the response will be an optimal proposal for, here's a new algorithm, here's some new parameters. That proposal should be optimal, but there is always uncertainty about what the patient prefers. So I will never know what the patient really wants, and the patient may also change over time, and the patient is moody and may not be consistent. So I'll never really, there isn't really an optimum. But what we can make optimal by Bayesian inference, and the word Bayesian, by the way, just means using probability theory. That's all it means. We can design the optimal experiment to do, or let's say the optimal next set of parameters I want to present to the patient. And it's optimal in the sense that it's the right balance between what we call in machine learning exploration and exploration, which means on the one hand, I want to make use of all the knowledge I have about the user and give him the optimal parameters, given everything I know about the user. On the other hand, I realize that I don't know a lot about, that there's still stuff that I don't know about the user. So I want to also do the experiment that gives me the most information gain, that allows me to learn more about the user, right? And that balance is sort of built in every action the brain makes. It's both information seeking as well as utility driven or goal directed. And that I can guarantee. I can never guarantee that we end up in the optimum of the user, but I would claim that nobody will ever be able to guarantee that.
There's a follow-up question from Sebastian Larsen. Related to the previous question, is there any chance of ending up in a bad local minimum that the user can't get out of again?
Theoretically, yes, but it's very unlikely. It's just because of the stochasticity of the whole process. Because we work with probability distributions here, let's say the answer that's given by the agent is not every time the same when it's in the same location. So it will eventually jump out and go to the next minimum, and then it will try to escape from that minimum and so forth. So it's unlikely that, let's say it's very likely that we can keep improving, although the at some point, the added performance by making experiments is not worth the cognitive load on the patient. You keep asking him questions. You don't want to keep asking questions, right? So at some point, you want to stop. You want to say, okay, I noticed, and we can of course measure the free energy. So we measure that. Hey, I'm posing questions and to the patient, he doesn't answer anymore, or his answers are inconsistent. So let's stop because we can't go any further.
Thank you. Related to that, and before we take the next question from Sebastian, obviously, how many interactions do you expect the users to have?
That depends, of course, on how large the parameter space is. It depends on how consistent the user is in his answer. He's very inconsistent a lot. If let's say if he just gives random answers a lot. The only thing I can guarantee is that the response of the agent is optimal because it's used on Bayesian probability theory, which we can prove is the optimal way of processing uncertainties or doing information processing. So I can guarantee that we do basically optimal experimental design here in sort of in a loop. That I can guarantee. How many times it takes, it depends on how far the current situation is from where the user wants to be. I think generally, just ballpark figure, for any problem with 5 presses of a pen, we should have an improvement. Otherwise, it's too much, right? So that's sort of and experiments that we do, and we haven't gone out with here. This hasn't been implemented inside hearing aids and walking around and everything, right? This is still in the lab. But in the lab, we always find within 5 button presses that there is an improvement. Let's say enough improvement for the user to say, stop, you know, I'm not going to bother. My current problem is solved, move on.
Okay, so you have basically been able to select some experiments that are tractable. That's what you can infer from that, because otherwise it would be probably they would run around answering questions that are not really leading to a significant
and
of the free energy.
I mean, the game here is that the perceived improvement should outweigh the perceived burden of interaction, right? The agent cannot do anything, but the best the agent can do is optimal information processing. It's a very objective task. It doesn't need to know anything about hearing aids. It doesn't need to know anything about personalization. It's just process all the information that you get as objectively and as precisely as possible and compute what is the best next experiment. That's what the agent does. There's nothing else. Then we should just this process is only useful when the patient feels like, okay, the 20 seconds that I need to do this, the perceived in the performance improvement is worth it. If it's and the process will stop if the perception of the patient is such that it's not worth it. Right. I mean, I've done this now a few times, and every time I don't really get the solution. So I'm done with this system. So that's our challenge, really. And I don't have real numbers on this. I mean, we are in the university environment. We are focusing on how can I build the best information processing agent. And this is quite an objective task, right? And everything else is really in the context of the hearing aid problem, but we're not there yet because, well, this is quite difficult stuff, really.
I think there's one more question from Sebastian Auseli. Also remember that in a short while, we will actually open the floor for actually having questions that you can either address to Bert or to Alessandro, or you can put a question to both of them if you want to hear two sides of the same story. But first, Sebastian has a question here. Super interesting research. More general thought. I also see many devices being automized in the future. At the same time, I understand hearing professionals being worried about of machines taking over their tasks. Once this technology starts growing, what are your thoughts on how actual professionals and these systems will work together?
Well, I mean, I think this is just, in a sense, just objective technology for how to design the best experiment. So I think everything related to counseling a patient on how to deal with hearing loss, everything related to this, all the psychological aspects, everything. Let's say also very difficult hearing loss issues will not be tackled by the methods that I develop, and not for a while, right? Over time, I think the profession of the engineer will change over time, because machine learning will take over some of that, and also the profession of audiologist will be affected. So I think, yes, technology that we develop here will over time change the roles of every professional in the loop, because we're changing the design loop. AI, the word says it, is artificial intelligence. You only need professionals, human professionals, for intelligence, right? Everywhere where you need some intelligent reasoning, in principle, AI could be useful. And so, yeah, and AI is going to be useful in the future, wherever we have intelligent professionals. So also here, that doesn't mean we don't need these intelligent professionals, but their roles will be affected, maybe in a good way, right? It's, yeah. I'm not sure if I answered that concretely enough. Let me just say one thing about this technology, because I don't want to. I know it's very on the surface, but I don't want to make it sound like it's completely abstract university. In Jabra, there's a Jabra product where you have an agent that sort of automatically takes your audiogram. That uses this technology inside, Frenetic minimization agent. So what we developed in our lab has made it to industry, but not yet for what I'm working on here, namely situated in the field design of hearing aids by the patient himself.
Thank you very much. Again, that was the last question directly to Bert. If you have some questions that you would put to the whole panel, feel free to do so. I would actually, related to your last comment, I would like to hear you, both of you, talking a little bit more about how far from being directly included in products is this, and where do you think that we can right now make some significant contributions to the field, where we can design problems that are worth being pursued and solved by using these techniques? I'll let you start, Alessandro.
Thanks, Nils, for the question. Related to my study, I believe that if complemented with additional relevant information about the patients, this could turn out to be useful, especially for the clinicians, because when being in the clinic and having to make decisions about counseling a patient, about helping a patient manage the hearing aids, knowing more about the users, knowing more about which type of user the hearing care professional has in front could be beneficial, especially if we manage to, for instance, make a predictive model that allows us to predict that a specific new user that the hearing care professional doesn't know much about is similar to another user that we know more about, both related to activities, preferences, behavior over time. If we manage to transfer like our learning about existing users to new users, that would be really useful for the hearing care professional to ensure that the first experience with the hearing aids of the new user is optimal, and also to make sure that whatever risk for a suboptimal experience is tackled early on in the journey of the patient.
Thanks. And you, Bert?
I think that let's say the agents that I work on, right? They in the beginning they will be used and just to learn fixed parameters in given algorithms, and the audiogram, finding the audiogram is an example of that. So that's working, and the next stage will be some other fixed parameter in a hearing aid algorithm, but hopefully in the field. Then the next stage is that that takes a bit more computation. You want to infer the parameters that whose optimal values change as a function of the acoustic environment. Now, it's not technically, that's no longer a parameter. It's a state. We also call that steering by the environment. When you go into a car, when you're in a car environment, you want to have some different settings than when you go to a cocktail party. And once you've trained it for the car environment, and you've trained it for the cocktail party environment, and you walk from your cocktail party to your car, you want it to switch back automatically, right? So this will be the next stage. I think we'll see that in the next 3-4 years. The next stage, and this is really the most difficult stage, is you don't want to just update parameters or states like environmental steering. You want to just train the entire algorithm. You want to learn what is the hearing aid algorithm, the optimal algorithm, the structure of the algorithm. That's what we're working on, and it's very hard to predict. But I know it will be there in 10 years, but I don't know if it's going to be there in 5 years or 7 years or 10 years, right? And it doesn't just depend on what I'm doing in my lab, but it also depends on, are there more labs involved in this? Is there going to be acceptation by hearing aid companies or other companies? Because it changes the industry a bit. And so there's a lot more involved than just the technical aspect. But I think over the next 10 years, there will be a slowly AI agents will do more and more in the design loop. The design loop of hearing aids is extremely expensive. With a few hundred people in the loop, it takes a few years. It's too expensive, right? We need to shorten the design loop, make it cheaper. And that's an AI really will help there. The endpoint, the singularity, if you will, is when the algorithm is designed, fitting is also automated and signal processing is automated. It's happening in the brain. The brain designs its algorithms for navigation, for hearing. It changes parameters. It changes your perception, which is basically the signal processing. It does everything automated, so it's possible. And we know kind of the underlying mechanisms, but to really translate that to workable engineering and to really translate that to workable products, yeah, there's a lot involved that so many uncertainties that it's very hard to predict.
True indeed. And let's get back to you and Alessandro in 10 years and see if those predictions actually hold. There's a high likelihood that we will be at some hearing conference in 10 years, and then we can get back to this. And this offer, of course, also goes out to all the participants that we had today for this webinar for the Danish Sound Cluster on personalization of user needs in hearing aids. And thank you, Alessandro and Bert, for some really inspiring talks, both giving some very concrete examples from the real world, and then afterwards Bert for taking us really far behind the scenes and getting this deep understanding of how this is optimally pursued with Bayesian inference. And with that, then we'll give the word back to you, Stine, and the Danish Sound Cluster from a few practical informations before we end.
Yeah, and thank you very much, all of you, both Niels for moderating and also Bert and Alessandro for speaking. Very interesting content indeed. And thank you also to all of our participants. We've had a broad audience with us today from the Danish sound industry, but also internationally. So that's really nice to see that it can attract some participants, but also that we have the opportunity to share knowledge, which is our purpose. Then I just need to inform you that we will send the presentations and the recordings to you after the session. And also please fill out our questionnaire as I reminded you in the beginning, because that really helps us improve the events in the future, and it takes around 1 minute. So that will be a big help. Please also watch out for our newsletter, where we announce events like this, both the webinars and physical events. We look forward to seeing you in other events and webinars. So thank you, everyone, and enjoy the rest of the afternoon. Hoping to see you again soon.
Bye-bye.
Bye-bye. Thank you.